Okay, this one's going to be kind of long. There's 16 slides. It's number sets. You've seen part of this already, so part of this is a review, but we need to be able to classify numbers. We're going to obviously go classify and order some numbers. We're going to talk about the different kinds of numbers are. So we'll start with natural numbers. These are the first numbers you'll learn about as a little kid. The symbol for those is that lovely N, right there, capital N. Natural numbers are your counting numbers. They do not include 0. So they are the numbers 1, 2, 3, 4, 5, and going on forever. If you can count it, I would say counting ducks, right? If you can count it, it's a natural number. We're going to have a Venn diagram. It's on the back of your vocab there. And we're going to put those in here. We're going to put our natural numbers in here. And you can see those go clear on the inside, your natural numbers. And you can draw in there. And I'm going to switch to a finer point pen here in order to make that happen. So again, 1, 2, 3, dot, dot, dot. Notice it's the most inner circle, all the way to the inside here. That means that the natural numbers are part of all the other number sets, with the exception of there's going to be something called irrational. But if something's a natural number, it's a member of all the other sets except for natural. So make sure you kind of remember that. I'm going to repeat that again too. All right, whole numbers. Those are the natural numbers like we just talked about, plus 0. Symbol for that's a W, a capital W. So again, what does that look like? So now it's 0, 1, 2, 3, 4, 5, forever and ever. No negatives, no decimals, no fractions. I mean, unless they're fractions like, let me give you an example here, by the way. Let's say 22/11. That's a fraction, but that's actually the number 2. So I can try to trick you like that, and I'm going to. But whole numbers, all the naturals plus 0. So again, whole numbers, they add on. So naturals were in here. Whole numbers include the natural numbers. So we add on that 0, right? 1, 2, 3, so on and so forth. So the naturals are part of the whole numbers. Okay, so add that onto your Venn diagram. It's that 0 that makes the difference. Okay, so integers are the positive and negative whole numbers. The symbol is Z. They don't use I because it looks like a 1. So the symbol is Z. So in this case, we're going to start out dot, dot, dot. -4, -3, -2, -1, 0, 1, 2, 3, 4, and dot, dot, dot forever and ever. Now the big trick here is to remember that I'm going to try to trick you. I will try to give you things like, okay, well, is -8/4 an integer? And you go, oh, no, it's a fraction. But then you realize, oh, that's actually the number 2. So I'm going to try to trick you like that. So please pay attention for that. I'm telling you right now, I'm going to try to trick you. So this time, we will notice, so here's my integers, and notice that includes the whole and the natural. So again, you're going to put dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, 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 forever and ever, right? There you go. Notice again, integers include the wholes and include the naturals, all right? So if something's a whole number, it makes it an integer automatically. If something's a natural, it makes it a whole and an integer. Now, before we move on to the next number set, I want to go over a couple of terms I'm going to be using. Terminating decimal. When converting a fraction to a decimal, right, remember the division, top divided by bottom, the division ends with 0. So terminating decimal examples are, so if I have 1 divided by 2, right, that ends up being 0.5, 0 technically if you like, right? 0.5, that's a terrible 5, there you go. If I have, let's say 1/4, right? So that's 0.25, 0 if you like, right? So it ends, it terminates. Any random one like 0.32, that ends. That is a terminating decimal. 4.387, it ends, so it's a terminating decimal. -1.9857. It ends, because you could put a 0 if you want to after it, right? That is a terminating decimal. It ends, it terminates. Like the Terminator, right? That's where that comes from. It ends everything. Robots are bad. Now a repeating decimal. When converting a fraction to a decimal, the division repeats in a pattern. For instance, I might have, I'm going to pick an easy one, 1/3. That's 0.3. You can put it in your calculator if you don't trust me here. 0.333 goes on forever and ever. Or we can represent that as 0.3 repeating, right? There's lots and lots of them. There's an infinite number of them. If I had, what if I picked, just seriously, just random here, I picked this 19/45. That means 19 divided by 45, right? So 19 divided by 45 is 0.42222 forever and ever. So we can represent that as 0.42 and just the 2 repeats. So those are examples of repeating decimals. They go on forever. Now, if something has a repeat pattern to it, so let's say it's like this, 0.637, 637, 637, right, forever and ever. That means you can have 0.637 with the repeating symbol. It can be represented as a fraction. There's a way to turn it into it. It's actually kind of a fun method. But it means you can turn it into a fraction, or it was a fraction at one time. So that's what a repeating decimal is. Now, a rational number. A number that can be written as a ratio of 2 integers. In other words, a fraction. Any number I can write as a fraction is rational. This includes terminating and repeating decimals. So for instance, just for argument's sake, simple one. If I had 14/7, that's really the number 2, right? So that's obviously rational. Notice that's also an integer and a whole number too, right? Yeah, there's a trick to this. So any number I can write as a fraction. Let me give an example here. If I give you, if I give you 0.2 repeating, right? 0.2 repeating. Technically, that is the number. I just had it in my head there. Is 2/9, right? 2/9. So believe it or not, it can be written that way, right? And you saw the example a couple of pages ago. We had 19/45. That can be written, it's a fraction, but it also is a repeating decimal. So rational includes natural whole integer and then the rationals. Remember, it also includes decimals that end. So like 0.4, right, which is really the same as what? 4/10. So that's 2/5, right? Same thing there. So those are rational numbers. I did forget to mention, by the way, on here, Q is the symbol for rational numbers, a capital Q. So again, this last set here that we've got, rationals. Notice that rationals includes all of my naturals, all of my wholes, all of my integers, all fall inside of rational numbers. So again, it is counting numbers, 1, 2, 3, 4. Whole numbers, right? 0, 1, 2, 3, 4, going on forever. The integers, so the negatives of those, -4, -3, -2, -1, 0, 1, 2, 3, 4, forever, ever in both ways. And rationals. And again, that adds on anything I can write as a fraction, or a repeating, or a terminating decimal. And again, all those integers, anything. And again, remember, I'm going to try to trick you. I'm going to throw in there, the number 18/9. 18/9. And you go, well, that's a rational. That's great because it's a fraction, but that's not an integer. What number is that really? Oh, yeah, it's really the number 2, which makes it all of these guys in this case, right? So I'm going to try to trick you. So be careful of that. Main thing to remember from here, if something's on an inner circle, like if it's here, if it's natural, that means it's also whole, also integer, also rational. Now something can be like -3, right? That'd be irrational. It'd be rational, not irrational. That'd be rational. So if I put like -3 here, but -3 is not also whole and not natural, but it makes it rational. You got to pay attention to the way that works. Okay, now a number set that is different from the others. It is not part of the others at all. Irrational numbers. Here's that capital I, right? I guess they do use it here. I forgot about that. There's another symbol. But anyway, numbers that cannot be written as a ratio of integers. Okay? So if it goes on forever, never repeats a pattern. I'm just going to make up a random one here. So -3.628597 Notice there's no pattern to this, and then if I go without a pattern, that's an irrational number. The one with which you are most familiar is probably the number pi. Okay? 3.1416, blah, 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 forever and ever, right? Never repeats a pattern. Those are irrational numbers. There's an infinite number of them, and you just make up any one you want to, but it does not repeat a pattern. It doesn't terminate, and it cannot be written as a fraction. Okay? Cannot be written as a fraction. So those go over here. So those go over here on the right on their own little box, irrational. And again, numbers like pi or 4.26879, dot, never has a pattern to it. So irrational numbers. Now then, we put them together, all together, and we have the real numbers. The set of rational numbers and irrational numbers combined, capital R, real numbers. Now, there are imaginary numbers. We're not going to talk about those this year because you're thinking, oh, well, that's all numbers. For our purposes here, it is all numbers. So every number we've talked about so far is an example. Number 1, the number 5, the number 4.2380, right? The number 1/3, the number -2/3, -4 and 5/3. Whatever. Those are all real numbers. So here they are. Again, real numbers is all these numbers that we've talked about so far in here. Real numbers. Everything from your natural, your whole, your integers, C is what I want, right? Your rationals, it's not an R, I don't know why I wrote that. It's a Q, right? And then real numbers is R, and then your irrationals over here. There we go. So now obviously you should have numbers filled in for that. Those are the different number sets. So there we go. There's one more slide after this, something else that's going to be useful. Just kind of threw it in at the end of this. Now I know we've already covered this here, this absolute value. As a reminder, what that is, it's the distance a number is from 0 on the number line. By the way, this is on your test. The symbol of these two parallel looking line things. So the absolute value of 4 is, how far is 4 from 0 on the number line? So if I had 0, 1, 2, 3, 4 spaces, so the answer is 4. Now if I said, well, fine, what's the absolute value of -3? You'd say, well, how far is -3 from 0 on the number line? It's 1, 2, 3, so it's +3. The only place this gets dicey is if I give you this. Now I'm going to try to mess with you, and you know that, right? If I said, okay, the negative of the absolute value of -2. We go, okay, well, absolute value of -2, right? How far is 2 from 0 on the number line? Is the number 2, right? So it is 2. But I've got this other negative sticking around the outside I got to throw back on again to make the answer -2 again. I'm going to do that to you, so please pay attention. I'm going to try to trick you. You know this about me. It's just the way it is.